What's up, everyone? This will be about a hour-long sort of lecture-style explanation of what is exactly going on with this this computer that I built, the JDH8. So I'm just going to be running it off of my screen up here, talking to the camera a little bit, and basically going through a more detailed explanation of the entire process of how the computer was built, because, you know, that doesn't really happen in a 13-minute video. But this is going to be much more off the cuff. I'm just going to try and give a basic overview, assuming a lot of knowledge about electronics, about software. Like, I'm not going to go through and explain like what binary and hexadecimal are and stuff like that, or like what integrated circuits are. But, you know, I'll talk about it for some, you know, above some base level of knowledge, I guess. But, you know, even if you don't necessarily feel like you have that, feel free to follow along and you might learn something as well. That in mind, I'm not an electrical engineer. I'm barely even a computer scientist, and not a particularly great programmer. So take everything I say with a grain of salt. You know, don't. I'm not going to purport to know anything, you know, serious about this. But I'm just a guy who hacked together a computer. So let's get started. So the first thing I want to show basically is, okay, I'm sorry about that. I just went into my terminal settings and made the font larger just to make sure that it's actually legible on like smaller screens and stuff like that. But anyway, we're going to get started with this, with an overview of the spec. So you can see in the top here, we have the overview, which is basically just a description of the computer. It's a mini computer, which means that it is not it doesn't use a microprocessor like an, you know, like the first microprocessors like the 8088 or something like that. So it's not one chip that is a processor. It is a mini computer, meaning it's designed out of like the processor is multiple circuits that are wired together. You know, like it's like a cabinet or a cabinet computer or something like that. It says also here it's designed to be implemented with TTL. It's actually not entirely true. These chips are, for the most part, CMOS. I don't know how you're supposed to say that, CMOS. There are only actually 2 TTL chips that are in the whole machine. So that's a little bit of a lie, but you know, it is like effectively the same as though we're implemented with transistor logic. My understanding is just like the voltage tolerances and the way the chips are designed is a little different. But anyway, mini computer designed to be implemented with TTL. There's an 8-bit data width, which means that its word size is 8 bits, so 0 to 255, or like negative 128 to positive 127 if you're operating in a signed space. It is a 16-bit address bus, which limits it to 64 kilobytes of memory, but that's not entirely right. As you can read here, it also has an 8-bit memory bank register, which allows for the theoretical addition of up to, you know, 256 memory banks. Actually only 254, because one of them in the computer is the built-in memory. The memory bank 0 refers to the built-in memory, and memory bank 1 refers to the video memory. But so 254 extra memory banks can be added. Theoretically, they could be RAM, ROM, they could be whatever, they could be a disk. But this allows for 16 megabytes of possible addressable memory, which is obviously more than this thing will ever get. This is actually a lie in the spec that I need to change. It was originally designed for a 4 megahertz clock speed, but in the end, because of the speed of the microcode ROMs in the machine, I ended up clocking it down, so it actually runs at 1 megahertz. I don't think that's not its theoretical max speed at all, but that was just an easy clock division for me to make. I just have the clock hooked up to a counter, and it counts 0, 1, 2, 3, reset to 0, right? So easy way to divide a clock by 4, and that's also used conveniently for sequencing operations as well. And then here we also have in the overview that it can also communicate with 256, actually 255, because device 0 is the status register, 255 devices. Currently there are none hooked up to it, but, you know, in theory it could be hooked up to whatever. It has a read and write channel with each device. Okay, and then let's get to the instructions. So the machine can do 16 different operations. It is designed around a load store architecture, meaning that basically it loads data from memory into registers, and then it does operations on those registers, and then you can throw the data back out into memory. But the only two instructions that interact with memory directly are the load word and store word instructions here. Then we have the move word instruction to move data between registers, and it can also move, Im8 stands for an immediate 8-bit constant. Similarly, Im16 is an immediate 16-bit constant, which is always an address. But so this move word instruction can move data from a register to a register, or from a constant into a register. Just load a constant into a register. And the format for these instructions is always instruction, or what's it called, mnemonic, then the destination, then the source. Okay, so the move word instruction, the load word instruction, the store word instruction, standard push and pop operations for the stack, which is this computer has a built-in stack pointer. It's done in one of the auxiliary registers, so it's not a traditional register it's accessible to, but built-in stack pointer, automatically decremented and incremented with these push and pop instructions. You can push immediates or registers, and you can only pop into registers, of course. It would make sense to pop into an immediate. Then we have the load address instruction, or LDA, which is technically re-implements move word, but it's a quick way to get an address into the H and L registers, which are the only way that memory can be addressed through a variable value, is through the H and L registers. So LDA basically loads a constant into the H and L registers using the H register as the high byte and the L register as the low byte. Then we have the jump if not zero, and I'll go over registers in a second. There are only 8 of them. But then we have the jump if not zero instruction, which is the only conditional jump instruction this machine has. It can either jump on a register value. So, if you say jump on register A, or jump not zero A, then it will only jump to the address contained in HL if the value in that register or that immediate is non-zero. So you say jump non-zero A, and HL contains the address hex F000. Then if A is 1, then we go to F000. If A is 0, then we don't, and we execute the next instruction. Then we have the two device IO instructions. These are in byte and out byte. These are actually not used anywhere right now, except for communicating with the status register, which actually the physical build of the computer does not have a status register. I didn't want to take the time to add it before I got the video out, but basically this is standard device communication. In byte, of course, reads a byte from a device. Out byte writes a byte out to a device. And the protocols are going to be, per device, of course. And then this is followed by the 1, 2, 3, 4, 5, 6, 7 arithmetic instructions. And these are all handled by the ALU. They are all very similar instructions, and they basically implement different arithmetic operations. And so the ones we have here are add, and then add with carry. And the difference here is that add with carry takes the carry from the last arithmetic instruction, or whatever is in the flags register, and uses it as the carry bit in an addition operation. And so that's what this plus C here denotes over on the side. Then we have standard bitwise operations and or NOR. These are, of course, you could implement everything, all the bitwise operations you would need with just NOR, but I decided to include and or also as their own instructions, basically just to speed things up a little bit, right? And because I had space in the instruction set to do it. Then we have comp or compare, which compares two values and loads the flags register. And then subtract, actually subtract with borrow, sorry. So addition, you can add without carry, and you can add with carry, but when you were subtracting, you were always using the borrow bit. So usually you'll see in a lot of the assembly programs for this computer that the subtract with, before subtraction is done, you clear the borrow bit. These instructions, these four denoted with this caret, load the flags register. So once they're done computing, they load the flags register with, well, let's move on to registers. These values down here, less, equal, carry, or borrow. And so now let's, look at the registers. So this computer comes with 8 registers, 8 built-in general purpose registers. There are actually more that are memory mapped. So A, B, C, D, and Z are all standard registers. You just move values to them and from them. That is it. They can be used in any instruction, you know. L and H are the low and high index registers. So they are the way that memory is addressed variably. For instance, if you want to get at the value in AB plus CD, what you would do is you would add CD to AB, and then you would take AB, and then you would move it into H and L, and then now you can address the memory that is pointed to by the pointer contained in AB, or the address contained in AB. So you always need to move into L and H in order to address memory. This is a silly design decision, but you know, I'll go over the bad parts of this design, I think, at the end of this video. And then the last and special register is the flags register. So flags is used to flags is used in a lot of the macros in the assembler, but it is used, it is reloaded by these 4 instructions: add with carry, compare, and subtract with borrow. Every time one of those instructions is executed, it loads the flags register by comparing those two, the 2 values that were used in the last instruction that loads flags. So less, of course, if you imagine this as add AB, right? Less would say that A is less than B. These are bits in the flags register. So the least significant bit is less. So less would say that A is less than B. Equal would say A is equal to B. And then, of course, you can infer greater based on that, right? If it's not less and it's not equal, then it must be greater. Equal would be, A is equal to B. Carry would be A plus B is greater than equal to 255. And then borrow is A minus B is less than 0, right? This calling convention stuff is only used in the assembly, so I'm going to skip it for right now. Now we have the instruction layout. So I'm actually going to pull this up in a side-by-side view so that you can kind of get the instruction layout. And can this fit? Yes, it can, just barely. Oh, but you can't read that part down there when my face is over. I won't talk about anything down there then. Okay, so now we'll move on to the instruction layout right here. And so the instruction layout is basically like, how are these instructions assembled into a way that the computer expects to find them formatted when it's loading instructions out of memory. And so you can see it's pretty clearly defined here. The instruction layout is, I defined it in, X, Y, and Z bits, right? Where you have 8 bits, 4 for X, 1 for Y, 3 for Z, where X is the 4-bit instruction identifier. And you can find that to the left of the instructions here. They go 0 through F, of course, 0 through 15 in binary, or hexadecimal or whatever. And then the Y bit determines, so all these instructions that use where the first argument is a destination register and the second argument is an immediate or a register, they use this Y bit to say, if the Y bit, bit number 4 is 0, then the argument is immediate. If it's 1, then the argument is a register, because it needs to be able to determine what that byte is, because the source value is always in the next byte of the instruction. So this is the first byte of the instruction. Is this XXXX, Y, Z, Z, Z. The Z bits are the register identifier of the register argument, which is always this over here, this destination register. So this is always the first byte of the instruction, but then you imagine, for instance, like, move word A, 28, right? Then then the first instruction ends up being like, I'll just write it out here in a place where you can read it. So move word is instruction 0. I'm writing it out in binary. So you have 4 zeros is the instruction identifier. You're moving a constant in because you're trying to assemble move word A 28, right? So you have 0 as your instruction, and then 0 because 28 is a constant, and then A. Actually, this is instruction all zeros. A is also register 0. So I'll use a better example in a second. So you end up with all zeros as your first instruction byte, and then your second byte is 28. So actually don't know off the top of my head what that is in. That's probably what? 16 plus 8. Is that wrong? No. Yeah, you have 16 plus 8 plus 4. I think that's 28 in binary. But anyway, this is how that instruction will be assembled. If we take like a more complex instruction or something like that, like LDA, for instance, is always hex 50. So it's 0101 as the instruction identifier, all zeros because those bits aren't used, and then the address. So this could be followed by hex FF if that's the address we want to load. This is LDA FFFF, and then we have let's take an arithmetic instruction. Let's take NOR, and then we'll NOR Z with F, right? And so NOR is instruction D, which is it one? No, it's not 1110. It's 1101, right? I think is D in hex, and then we have it is a register. The second argument, this F over here, is a register. So that means the Y bit is 1, and then Z is register 6. So that means we have 420 there. So this identifies Z. This says that the next argument, the next byte is a register, and then this says that the instruction is NOR. And then, of course, the next byte just contains F, so it says 1, 2, 3, 4, 5 zeros, and then 1, 1, 1 to identify F. So this is how you would assemble that instruction. Or, right, it's like hex D E hex 07. Okay? And then I'm not going to go through how if you're interested in looking at how the memory instructions are assembled, you can just go look at the assembler. I think the source code is pretty clear on how that stuff is done, or you can read through here. Anyway, though, so moving on to memory layout. So now that we know how instructions are assembled, where are we getting the data? What does that look like? So this is not necessarily a constraint of the architecture. This just happens to be contained in the spec because it's very relevant to how the machine was built. But so, yeah, here's the memory layout. So, of course, it is 16 bits. So we go from hex 0 to hex FFFF. And you can see in here the memory mapped registers, which I'll explain in a second. So the first 32 kilobytes, sorry, are general purpose read-only memory. So this is where the operating system is loaded. The computer starts executing from instructions from address 0. So the operating system is on this ROM. Library functions can live on this ROM. Sort of whatever. But the key is that it is read-only memory. It doesn't necessarily need to be, but I don't really see how else you would load programs onto the computer. If you're starting up with some RAM or something like that with garbage in it. Next we have from hex 8000 to hex BFFF, we have, and these are inclusive, by the way, these ranges are inclusive. Then we have banked memory. So this is memory that corresponds to the memory bank register. So the memory bank register is a built-in 8-bit register that is memory mapped at address FFFA. So you can read and write to it as though it were just a memory address, but that is actually the memory bank register. And the value in there determines which memory bank that the computer is using right now. So memory bank 0 is just standard built-in random access memory. Memory bank 1 is video memory. And then, you have 254 more memory banks that could be used for whatever. It's theoretically extensible as much as you want it to be. So that's banked memory. Then after that, you have 16 kilobytes of general purpose RAM minus a little bit, because the top is chopped off here because of these memory map registers, but about 16 kilobytes of general purpose RAM. This has not changed with the bank. Then we have a recommended place for the stack, a little more general purpose memory, 8 bytes of it, I guess, or 9 bytes, no, 10 bytes, 10 bytes of general purpose RAM. And then you have the memory mapped registers. So this is the memory bank, as I just explained, is at address FFFA. FFFB was the memory bank used to be a 16-bit register when I was designing this, but I decided to make it an 8-bit register when I was actually building the computer, because you don't need to be able to address 32 bits of memory theoretically, and you're not going to have more than 254 extra memory banks on this thing. But anyway, so that means FFFB is unused. FFFD is the stack pointer, or sorry, FFFC to FFFD is the stack pointer. So this is a 16-bit memory mapped register where the 16-bit values are treated as little endian in this machine. So that means FFFC contains the low byte of the stack pointer, and FFFD contains the high byte of the stack pointer. And then here, we have the program counter. So that's FFFE to FFFF is the program counter. Standard stuff, it just keeps track of the current instruction. Yes. Memory banking, that was already explained. Ports, the computer includes a status register at port 0, which is how the halt signal is communicated. So halt will stop the clock. I decided not to implement this in the physical machine. Then here we have a little explanation about the video deal. But I'll just mention here, like I said in the video, it's 208 pixels across by 240 vertical pixels. It uses the same clock as the rest of the machine, and it communicates with the machine through the video memory. If you want an explanation about how this was done, I mean, you can go read this. You can go read a lot of resources on it, but it is not within the scope of this video to explain that. So next up, I am going to go through, so after I wrote the spec, the next thing that needed to be done was, well, you need a way to write programs for the machine, even if you're going to emulate it or something like that, because hand assembly takes a while. So the next thing I did was I wrote an assembler for this machine. And this isn't all the source code for the assembler, but maybe we'll look at one of the tests. So the assembler basically takes programs written in the assembly language, kind of defined in the spec, and then will assemble them into executable binaries for the machine. It just dumps out the instructions in order. But it's a bit of a fancy assembler, because not only can it assemble like a program like this, but also you'll notice, this includes some things that weren't in that instruction listing, like CLB and halt. And these are actually built-in macros for the assembler. So if we look in here, we can see this huge list. So 16 instructions isn't a lot of things, isn't a lot of operations. And, it's kind of smart to group more complex operations that are done a lot into macros, where, instead of saying, for instance, here's a really useful one, call, right? This pushes the current address to the stack and then jumps to another address so that ret can return to where a procedure was called from. So you obviously don't want to write this out and calculate it by hand every time you need to call a procedure. So this is a really good example of the macro system, where basically what it does is anywhere you write, say you're writing in some assembly program and you say, call this procedure I want to call, right? And you don't know, the address of this thing, but what happens is this procedure I want to call gets expanded into, automatically by the assembler, into here. So it does this math to the address, right, of the procedure you want to call. It pushes, or sorry, that's actually not true. So it does this math to the current address denoted by this $sign, saying basically pushing onto the stack where we want to return to. Then it loads the address of the procedure that you want to call, and then it jumps there, right? And this is way easier than using a macro for this, right? Instead of writing all of these lines, we just have this call this procedure I want to call. And of course, macros can be, they can depend on each other. So you can do stuff like, I guess ret is also a good example of this, the return macro. So pop L, pop H, and then jump. Well, there was no jump instruction. There was just jump if not 0. So jump is actually JNZ1, which is just an unconditional jump, right? Jumps to the current address in HL. Yeah, and basically you can see a bunch of macros in here that are built into the assembler. They're loaded every time a program is assembled. There are a bunch for 16-bit arithmetic. Some of the simpler arithmetic, this won't do multiplication or division or stuff because on this hardware that needs to be implemented with loops. A lot of stuff for interacting with 16 bits. Different jump macros, which are quite useful. So you can say, instead of just always jump if not 0, you can say, jump if less than, jump if less than or equal. And you notice these are implemented with different arguments, right? So this one only jumps to an address. If the bits in the flags register are set to be less than or equal, this one compares against either a register or an immediate, denoted by this %x1. Yeah, and then we have a bunch of things to make it easier to push and pop multiple registers at the same time. And this halt macro that I mentioned earlier, which reads in the current status byte, sets the halt bit, and then writes it back out, which will, halt the machine. And I also mentioned the subtract without borrow. You can see it's CLB, which is another macro that clears the current borrow bit in the flags register, and then subtract with borrow. But of course, the borrow bit is now set to 0. And so, yeah, so basically we have an assembler that can assemble all sorts of fancy programs. It also has the assembler itself has macros in it, like this include, or directives, I'll call them to be more clear, like this include directive here, or if you go here, it has, like in C, it has if not defined and if defined, and the define macro for defining, textual substitution constants, just like in the C preprocessor. But yeah, basically, this makes for a really nice assembler. And it makes it much easier to write programs for such a limited computer. All of the programs, if you go look in the GitHub repo, are just full of using macros because it just shortens up how things are written. It makes it much easier to understand. So, okay, moving on from there. So I wrote the assembler. I won't go over the emulator because that is just it is just an emulator. It just emulates the machine. If you want to go look at how that worked, you can go look on the GitHub repo. Same with the assembler. It includes its own lexer and parser and things like that. They're relatively simple. But so to focus on actually how the machine is made, next up I will move on to the circuit, or how this thing was actually built. So I'm going to open it up in Logisim, if I can get Logisim to open, which I hope I can. My Mac is telling me that it doesn't want to open it. Okay, here we go. And then here is my slightly modified copy of Logisim Evolution, in which we can open, if it will open, here we go, the computer circuit. So designing the circuit for this computer, I knew from the start that it needed to be segmented into different modules. And those you can see here on the screen, right? We have the, registers, which contain all the registers I just mentioned, auxiliary registers or aux regs, which contains like memory bank, stack pointer, program counter. ALU does all the arithmetic instructions, address calculates the current address, op counter keeps track of the current instruction and where we're executing in it. And then control, you can see out here, controls the entire machine. It controls all these signals based on the current instruction. And then you have RAM and ROM. So going through and designing this, basically, you can see here all the submodules are just, they're standard circuits. I mean, they basically just contain registers combined with a bunch of combinatorial logic, multiplexers, demultiplexers, in order to properly execute and sequence the operations of the machine. I'm not going to go into like really, really deep detail about any one of these, but maybe, this one's a little complicated. Maybe just as a basic explanation, we can go through. The ALU is probably a good one, right? So here is the circuit design for the ALU, what it needs to look like and what it needs to be able to do. So we have these control signals. So the op is the current operation. The clock is the clock signal. We have a load X and load Y signal. Enable ALU, which means the ALU needs to push its current current calculation onto the data bus. LDF signal, which means push flags onto the data bus. It has data in coming from the same data bus, and F in, which is the current value in the flags register. So you can see here, basically what the ALU does is it has these two registers, X and Y, inside of it, that can take data off of the data bus, load it in from here, and then when clock and LDX or LDY are triggered, it takes the current data off the data bus and stores it. So you can imagine that an instruction that needs to be executed by the ALU would look something like, or the sequence of operations will be like, okay, we need to add two values together. So get the first value and put it in the X register, then get the second value, then put it in the Y register, right? So first bit is LDX, then do an LDY. Then we need to get the value out. So we use the EALU signal to push the value onto the data bus and send it off to its destination. And then LDF, of course, if we're adding 2 bytes, right? It will always load the flags register if you're adding things. And then LDF, load the flags register, right? And so then you can see how this is implemented here. Basically, you take the values in the X and Y registers, they go through AND or NOR, compare, subtract, add, right? And this was basically done for all of these different circuits. Register is also quite simple, literally just contains the registers and some logic to figure out which register we want to be putting out onto the data bus. The aux regs is a little more complicated, but because it includes counters and stuff like that, but I'm not going to go through that. And then we have also the video circuit, which you can go watch a video on the video circuit that I did if you want a better understanding of this one. But basically, I guess I'll go through now, basically. Right, so I was saying as you're executing the instruction here, it needs these different signals in sequence, right? It needs LDX, then LDY, then ELU, then LDF. And each one needs to have its own clock signal. And you can imagine it's kind of hard to, if you have 16 different instructions, then you need to do different things for each instruction. It's kind of hard to have combinatorial logic, just logic gates that say, okay, first, if we're doing an add and it is the first clock cycle of that add, then we need to do an LDX. But if it's a second clock cycle, then we do an LDY. And if it's a third, then we do an ELU. But actually, that LDY needs to come from an immediate if the immediate bit is set. And you can imagine this gets really, really complicated really fast. And so the solution to this, and Ben Eater I think has a fantastic video on this, is to replace combinatorial logic with EEPROMs. And so this is what microcode is. So basically what this does is instead of asking some combinatorial logic, oh, we're doing an addition operation, and it's a register and an immediate, and we need to find out what to do, and it's the the third clock cycle in this instruction after it's been loaded. What we do is we just combine that stuff into an address for, where is it? An EEPROM. And the EEPROM says, you can see the exact same LDX, LDY, LDF, EALU signals right here in the EEPROM. The EEPROM says, okay, I know that you're executing this instruction, and the argument is a constant or a register, and you're on this stage of execution. That turns into an EEPROM address, and then the EEPROM says, programmably, what to do for this part of the instruction. It also says when to stop. That's this CC signal here, or when to stop and when to load the next instruction. And you can see here that microcode. So you'll notice these correspond exactly to these signals here. That microcode is assembled by the same assembler. It just uses this @microcode directive to say we're assembling some microcode. You can see for every instruction here, it also uses macros actually. For every instruction here, it says what signals to do. So for instance, if you're doing a move word instruction and you're moving a constant into a register, what you need to do is, what the computer needs to do for the first and only execution cycle is enable op1, so push the second byte of the instruction that was just loaded onto the bus. Not cell says basically use the register selection that's contained in the first byte of the instruction. These signals can all be inverted to say do this or don't do this, right? And then lreg, which says load the register, which register, the one that not cell says, which says the register that is denoted by the first byte of the instruction. And then you can see here the way that move word is implemented for a register to register move. What you do is you push the register onto the bus out of, positive cell, which means the register pointed to by the second byte of the instruction, and load y, which says, load it into the y register in the ALU actually. Then EALU will pass that value through from the y register. Not cell says select the destination register. Load reg says load into the selected register the current value on the data bus. And you can see here enable memory, load memory. Those are memory interacting instructions. All of these A prefixed by and then suffixed by something else. Those denote which address should be used. SPDEC and SPINC, they're stack pointer increment and decrement. EOP1 and EOP2 say push the second byte and third byte of the current instruction onto the data bus. This basically controls how the entire computer works. And you can notice down here for the ALU, you have those LDX and then LDY and then EALU and then LDF signals in sequence, right? And then the microcode assembler automatically says, okay, if this is the last microcode instruction in the sequence, then also tack on this CC signal that says, we're done, load the next instruction, keep going, right? That's basically how this computer avoids being even bigger. And so basically, you have each of these modules, and then the next thing after all that was solved, right? After you have this whole computer wired up in Logisim, is to convert it into a format that can be built with these. Let me see if I can adjust my focus properly. These little 74 series integrated circuits. Then I'm going to get myself back in focus, I hope. Now, those little 74 series integrated circuits. And so, obviously, this stuff doesn't look anything like a 74 series integrated circuit. There's no, I dropped that one on the floor. There's no mapping, or no clear mapping at least, between this stuff and one of these. And so what we do next is we convert it, and you can probably already see here in the sidebar, we convert it to all of these 74 versions, which are, you know, basically the same circuits. Like you can see this is the ALU. So this is this circuit, same inputs, same output, but implemented using these 74 series integrated circuits. You know, you can see a bunch of buffers down here, but you see some you recognize, right? You can see AND gates, NOT gates. You have adders here, comparators, AND, OR, NOT over here. You have some buffers, demultiplexer. Right, and so the next step is to take all these modules, convert them into these 74 series versions, and then plug them back into, where is it? Yeah, here, plug them back into the exact same circuit and say, okay, does this still work, right? Are these 74 series implementations of these circuits, or in this simulator, actually doing the same operations as their equivalents, right? Their equivalents in like the fancy circuit, you know, notation, right? And so after that was done, all this stuff, I'm skipping over like many hours of work. You know, every time I say, you just converted into, you know, these 74 series stuff. This took a little bit to design this out. Especially because there's not a clear one-to-one mapping for all of the circuitry and stuff like that onto these 74 series stuff, especially counters. Counters were a real pain to be able to get them to sequence properly when transferring into the 74 series world, I guess. So once you have all that stuff together, you know, you have all of your 74 series units, modules, then we combine it all together into this huge circuit that is basically showing what needs to be where on every breadboard with every single marked signal. And, you know, this is basically just the whole computer. And then you make sure that this whole thing works, right, in the simulator. And so once you have that, though, this is kind of a pain to work with. So the next thing I did, basically, was I took the whole thing, and if you watched the other video, you saw this. I took the whole thing, and let me do this to make it a little clearer and maybe zoom a bit, and I color-coded it. So you can see this is that entire schematic exported out of Logisim, then color-coded, and then organized nicely, basically, so you can see to which module each of these circuits belongs, even if they belong, you know, partially to some modules, partially to others. You know, there's a lot of that up here with sharing the same circuits, right? And then, yeah, every signal in here is labeled and where it needs to go. And, you know, this was kind of designed so that hopefully there wouldn't need to be a lot of cross-board wires. But, you know, that didn't end up really happening. There are a lot of cross-board wires in this whole thing where wires need to go, where wires need to go across modules and stuff like that. Sorry, I bumped the microphone there. Yeah, and so basically after that, you know, you just get the circuits or I got the circuits and I wired this thing together. You know, and that's what's sitting over here to the side of me now, that, you know, I can try and get the camera on maybe. I might just overlay some footage here or something like that. But yeah, basically that is how this whole thing was designed and then built. Additionally to those other modules, you can see down here, there's these little buffer circuits that are just used to buffer for some LEDs, which will show the current execution state, control signals, and a data bus value of the machine, you know, that were really useful for debugging. Yeah, and that's the whole machine. But so, of course, when I wired it together, it like absolutely did not work at all the first time. Of course not. I made a ton of mistakes, and I forgot to wire a ton of things, and a bunch of wires were in incorrect locations, and I short-circuited the whole thing a few times. Right, as you do. With this much stuff, you are bound to mess up at some point. And so basically the last thing I want to kind of show here is the debug program that I used. So thankfully, all of this stuff could actually be powered off of an Arduino, which was nice because it means that I could hook it up to my computer, and I could, where's my program? Basically means that I could hook it up to my computer, and I could, where is this stuff? Here. I'm just opening up the little Arduino IDE. I could hook it up to a computer, and then I could manually control how many clock cycles it got. And then using those LEDs, I could say, okay, I know that I've loaded into the ROM, say, a program that loads this address and then jumps to it, right? And then I can step through on the clock using the Arduino and basically, check on those LEDs physically that the computer is doing the right thing, that it's receiving the correct control signals. And then also, I can go around and stick some wires in to make sure that the internal control signals in the computer are also working correctly. And that was my primary mode of debugging, basically. It was done through this program where basically the Arduino connects to the serial monitor, and then every time you hit enter, it ticks the clock 4 times, which is 1 more CPU cycle. And then you can say, okay, what is going wrong here if the instruction isn't executing correctly. And you can just look at the LEDs and, try and hopefully debug the entire thing. So I spent about a good 20, 30 hours doing that because I made a lot of mistakes. But yeah, that was basically how the machine was designed. I believe I've covered everything. I'm just going to check here if there's anything that I possibly could have missed, but I don't think so. Really, if you want to go see what the a lot about how this computer was designed and stuff like that, I would recommend you go take a look at the GitHub repo. You can go look through all of these assembly files to see some more complex programs that were written for the computer, not all of which I ended up running on the physical machine so far, at least, because it doesn't really have a keyboard connected to it, so it's not that fun yet. It can just do calculations where it's almost like punch cards or something like that, right? You load it onto a ROM, and then you stick the ROM in the computer, it outputs the calculation, and then you can't do anything with it. It's a little unfun. But yeah, you can see all these assembly programs written for this computer. You can take a look at the schematic. If you try and open the Logism file, it actually won't work for anyone. And that is because there are about 25 integrated circuits that I added myself to Logism Evolution because I was missing them, that I am maybe going to PR into Logism Evolution at some point. It would be a big PR and it would take a little while, which is why I haven't done it yet. But that I might add them if I feel like I have the time or desire to at some point, because it doubles the number of 74 series ICs that are in there. But there were just a lot that I needed to use in my project that I knew existed that weren't in Logism Evolution. But yeah, basically, if you have any questions, write them down in the comments or send me an email. I don't always answer my emails, but you can find it on my channel page on YouTube. I'll try and answer them. And then, of course, if I live stream later on or something like that, you can ask me a question there. But I hope this was an acceptable explanation of this whole project, kind of from top to bottom. Obviously, I skipped over a lot, but it was a lot of hours. So I can't exactly take you guys through absolutely everything. But basically, yeah, thank you for following me throughout the duration of this project. Thanks for 100,000 subscribers. You can see my play button sitting back there. Yeah, I hope you enjoyed the video. I hope this explanation was kind of helpful for some people who, you know, don't exactly know enough about the area or the field to dip their toes directly into the GitHub, but like, you know, will do a little better based on just like an auditory explanation or something like that. And yeah, I hope now you can go look at the stuff on the GitHub because, you know, I'm pretty proud of it. So yeah, I think with that, thank you for watching this video. Go check out my other videos on this computer if you haven't seen them, and you know, see you in my next video.